Well, we're going to start the section 3, unit 3A, section 1. This one's we're going to do two things. One is primarily the definition of derivative. We've done this before. This is a repeat of what we did in unit 2. And the second thing we're going to do is look at the graphs of derivatives. So two objectives here. First, let's talk about notation. Um, the derivative, which is instantaneous rate of change. Um, and also slope of the tangent. They're all the same thing. Notation is given by f tick x or f prime x, which is the same thing as y tick or prime. Please don't go to college and call it tick. It's prime. And then the last way is we take the derivative with respect to y. I'm sorry, the derivative of y with respect to x. That's how that's to be read. So it's the derivative of y with respect to x. It's important as we go along that you understand that notation. Uh, these two, this one does give you with respect. It tells you it's with respect to x, and this one does not. It's just a simpler, abbreviated way to do the problem. The derivative, which we've already seen, by definition, we're going to learn shortcuts here shortly. We get to learn those in section 3, but the derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. And you'll get a 0 over 0 for those, you always do, and those would also imply there's a cancel factor, and it's something not new. There's also another one that you may use if they give you at a point, say at x equals a. Then the new form we can also use is the derivative with respect to x. Again, notice how I'm reading that. It's important. At, see the line? It means at x equals a is equal to the limit as x approaches a of f of x minus f of a all over x minus a. Obviously, this one is very clear. This is slope. But the idea is the a gets real close to the x, infinitely close to where we're almost at a point. Okay, so what is a derivative? A derivative is, we've stated this before, is the slope of the tangent line, or quaintly called the mtan. And it's also, application purposes, is instantaneous rate of change. Okay, so examples. This is, we did some in our last assessment. This is not something new, but we obviously are not the master of it yet. When it says definition by definition, I have to use the limit as h approaches 0 of f of x plus h minus f of x all over h. And as you've seen with the fractions, whenever you're subtracting subtractions, common denominator, and instead of dividing by something, you can multiply by its reciprocal. So we're going to use those two skills here. So I'm going to take this guy and I'm going to go limit. There we go. H approaches 0 of 1 over x plus h plus 1 minus 1 over x plus 1. And we're going to get the common denominator. So we're going to multiply this by x plus 1, x plus 1, and this one by x plus h plus 1, x plus h plus 1, all over h, which equals limit as h approaches 0 of, now what I'm going to do is I'm going to write down my common denominator, because I'm not doing anything there, I'm just copying it. And then instead of dividing by that h, by this h, I'm going to multiply by 1 over h. And now let's take care of the top of my numerator. So x plus 1 distribute negative 1 gives me minus x minus h minus 1. Conveniently, if you've done this correctly, your x plus 1 will disappear. There it goes. Leaving me with simply limit as h approaches 0 of negative h over. Now, don't FOIL this out because you're just going to make a very ugly thing even uglier, and then cancel your h's. So the m tan, or the equation for my slope, is negative 1 over x plus 1, x plus 0 plus 1, because I took the limit now, which of course leaves me with negative 1 over x plus 1 square. Shortcut, we'll see that work. But right now, we're just using the definition. And they notice up here in the original question, they don't give us at a point. That's why I had to use the f of x plus h minus f of x all over h. Okay, now, second objective is to learn to graph. Something to notice about these things, especially with polynomials, is the relationship of the power and what happens to the power. So basically, we're going to start with the premise we don't know anything about these derivatives. And like anything else we graph, we're going to sketch and plot points and then connect the dots. So anytime I don't know anything about a graph, I simply pick some points, plot them, and then sketch it. So what I'm doing here is I'm going to graph the derivative, which means I need to graph the values of the slopes. So I want to make a table of my points for my slope, my derivative. So I'm going to pick a point. There's negative 2. Find its slope. Now again, this is going to be approximate. So I'm going to say the slope there is negative, let's say negative 4. It doesn't have to be perfect. At negative 1, the slope appears to be negative, let's say negative 2. At 0, my slope is 0. Here, my slope is, well, you can see the symmetry between the two sides. These two things have symmetry. So if I called that negative 2, this side negative 2, this side has to be positive 2. And then same way with the last point at 2, I'm going to use 4. Now, if I plot those points, just like I would anything else, I don't know what it looks like. Negative 2, negative 4, negative 1, negative 2, 0, 0, 1, 2, and 2, 4. Connect the dots. And I have the sketch, or I have the graph of the derivative. Observation. This appears to be a power of 2 polynomial. It is a parabola. Notice this one appears to be a power of 1 function. Actually, this looks like 2x. It doesn't really matter much exactly what it is, but the relationship's there. Notice that the power got diminished by 1. All right, next one. I'm going to erase to give myself some more space here, and I'm going to make a table. And this time I'm going to be real careful. I want to observe and note when I'm making these, picking these slopes, where they change, where there's significant change. Like if I look over here at negative 3, there's clearly a negative slope. I'm going to say that's negative 4. Not relevant exactly what it is. But then right here at negative 2, it goes to 0. That's a critical point. It's where the derivative is equal to 0. It's going to be referred to later as a critical point because it is critical. Okay. Next one. At negative 1, excuse me, it appears that the slope is 1. Again, another critical point. At 0 is slope is 0. And I continue that process all the way through. At 1, it appears to be negative 1. At 2, it appears to be 0. And at 3, it appears to be, again, symmetry is involved. If this I called negative 4, I'm going to call that 4. Plot your points. -3, -4, -2, 0, -1, 1, 0, 0, 1, -1, 2, 0, 3, 4. Connect my dots. Observe that since the original curve was smooth, its derivative must also be smooth. Again, also, I want to note that this, because of the number of loops, this appears to be a fourth power. Notice this is a cubic, power of 3. Notice the dimension of the diminishing of the power. This is a very common question, this next one. This next one is actually the leveling off. It has a carrying capacity function. It's well noted for its application because a function that increases and levels off is kind of like putting rabbits on an island. Eventually, you can only fill so many rabbits on that island, hence creating an asymptote right here. And I want to note those two asymptotes right now. This asymptote's the applicable part here. This one, not so much, because generally this area here is negative. The left side is negative, and it's not, we don't apply it much. Okay, so what I'm going to do again, I don't know what this looks like, so I'm going to go ahead and note the slopes, and I'm going to plot those points. So if this is asymptotic, it really never goes to 0. So what I'm going to do is I'm going to pick a point over here like -3, and it's not really 0, it's asymptotic, so I'm going to pick a very small number. I'm going to make it so I can actually sketch it, so I'm going to call it 0.1, even though it's not. And note each time as I go this direction, the slope gets smaller. Then I'm going to move over here at -1. It appears to be 1. At 0, it appears to be a little bit bigger, maybe 2. At 1, it appears to be smaller again. And then something way out here at 3, it appears to be real small. So at 3, let's just say it's 0.1. And notice, again, the slopes keep getting smaller, but never get to 0. Okay, so let's plot those points. -3, really, really small. 1, no, sorry, -1 is 1. At 0, it's 2. At 1, it's 1. And at 3, it's 0.1. Now, I can connect my dots, but what happens, and this is incorrect why it's red, is people tend to do something like this. There's an issue with that. Notice this implies the slope over here. It's saying the slopes become negative. Anywhere along here, do you ever notice the slope being negative? I don't think so. Nowhere they're negative. So it's very important that when we consider this curve, we consider those asymptotic relationships. So I'm going to sketch this guy, but as I go along, it's going to be smooth. But down here, the slopes get smaller and smaller and smaller, but never get to be 0, as observed over here. And this one comes down symmetrically, and the same thing happens here. The slope never gets to be 0 over here. It approaches, but never gets there. That's why I never let it touch the 0 line, creating an asymptote here. So asymptotic relationship for your function creates an asymptotic relationship for your derivative. Again, that's a key one. Now, there's something weird going on here. We're going to get to that in a second. So let's take a peek at this one. Let's create those slopes and get those values. If I look at this carefully, every single place, any x value I pick along here, all the slopes are the same. They appear to be okay, well, I apologize for the interruption, but apparently my wife is calling. Sorry about the interruption. Okay, so we're doing the last one. Notice again what I was talking about is the slopes here all appear to be exactly the same. So if I pick -3, -2, -1, they all appear to have a slope of +1. So those are all the same values. But Then over here at 1, 2, 3, 4, 5, all the slopes appear to be 0. What happens here is very odd. Let's plot this real quick. I'm going to plot my points. -3 is 1, 1, 1, 1. And then all of a sudden it's down here. Remember I used the word smooth? Notice this is not smooth. This is a corner. It's going to create a non-differentiable point. Basically what that means is when you come along here, the slope gets here, but it tries to get to be right there at 0, but it can't. Because it all of a sudden jumps down here, creating a jump point of discontinuity. So my actual graph of my derivative is a step function. That's it for this one. I will post up every single one if I can. So hopefully that was worth your while, and we'll go through the questions, which will be posted in Google Classroom.